We'll start today talking about the AC machines. And when we say, of course, AC machines, similar to what we did with DC machines, we're talking about the electrical side. Now it's going to be AC, so alternating. So whatever voltage and currents we are using in the motor case as an input will be now AC. And the voltage currents at the output of the generator, AC generators, will be alternating also AC. And this is a little bit more practical because we know that our power grid is AC. So we generate AC electricity using AC machines. And also we consume electricity using AC motors. Doesn't mean that DC motors or DC generators, they don't exist in the system. Yes, they do, but much limited applications if we compare it to AC. So basically in DC, we discussed the structure of the machine, how the basic operational concept, etc. And after that, different types and connections. We're going to build on that knowledge because AC machines, they are similar in DC machines. And let me just remind you about DC machines. In DC machines, we have armature winding and field winding. The armature is located on the rotor and stator, and the armature is located on the rotor and the field located on the stator. We have either separately excited or self-excited, but for separately excited, we excite the machine, we provide the field using separated circuit or separated source like a battery. So there would be a magnetic field provided by the field winding using external source. And in the generator case, we have the input as mechanical. So the mechanical input will be provided also by external source. So mechanical input, magnetic field, the result is, and we explained this last week, the result is voltage induced, EA. But the voltage induced across the armature windings or armature terminals is what? AC or DC? It's AC. It's alternating, if you remember the discussion at the beginning of the chapter. But using the combination of commutators and the brushes, they only collect one side of the voltage. So across the brushes is DC, but across the armature terminals is AC. That's it. This is basically the DC generator. So if I ask simple question, how we can design AC generator, someone actually might come and say, well, it's similar to the DC, but simply we don't convert from AC to DC. We take the AC as is, which is true. This is what we do. So if you understand the DC basic operation concept, basically you can understand easily the AC, because the only difference will be how you collect the voltage from the armature winding. There are a few other differences, but again, there are many common things. For example, we still have armature, we still have field in AC machines. We still have rotor, we still have stator on our AC machines. Same basic operational concept, something rotating, some stationary, magnetic field, voltage induced. But we don't convert from AC to DC. So today we're going to talk a little bit about the basic structure of AC machines, the basic operation concept. And we're going to start with what's called synchronous machines. There are two types of AC machines. One is called synchronous and the other one is called induction. So we'll start with synchronous machines, and next week we'll talk about induction machines. So for synchronous machines, and I'm going to talk also today what's the meaning of synchronous here.
Doctor, I'm sorry for interrupting, but can you upload the slides? Because I am taking notes in the slides.
I will try to upload them as soon as I revise them and make sure that they are correct. So inshallah, I will try today or tomorrow maximum, okay?
Okay.
So asynchronous machines is an AC machines, as we mentioned. So we're going to talk about synchronous machines in which alternating current flows in the armature winding. And DC excitation is supplied to the field winding. So again, AC current and voltage in the armature. What about the field? Well, field will be similar to before to the DC machines. Field will be DC supplied by a DC source. You remember separately excited machine where we supply the field by using external DC source? Yeah, it's still the same. So the field will still be DC, but the armature will be AC. So this is a major difference. The armature winding is designed to carry large currents at large voltages. So yes, this is from the application. Usually in AC machines, the armature designed such that they carry large currents at large voltages. And this is important. Why? Because now, because the winding is carrying a large current and large voltage, and because usually we design AC machines to be three-phase. So how we design a three-phase? Try to remember. If we want the machine to generate three phases, how many windings we use inside the machine? 1 or 3?
3.
3. So the armature windings will be 3 instead of 1. Because now we want to collect the 3 different voltages. They have the same magnitude, but the phase shift 120 degrees. So in AC machines, we need 3 armature windings. In DC machines, it's only 1. In AC machines, we usually have large current and large voltage in each of these armature windings. So what does that mean, the large current, large voltage? So large current, what's going to be different now in the wires, for example, if it is large current? Wires
The losses will be low.
No, it's not about the losses. It's about the size of the wire itself, right? If the current is large, so you design the wires to be also larger to carry the large current. If the voltage is large, you design the insulation to be also larger. So again, because of the 3 phases, we have 3 windings. Because of the large current, we have larger diameters of the wires and the wires. Because of the large voltage, we have more insulation, let's say. So imagine that you have 3 windings, large wires, more insulation. Where you would prefer to put all of these 3 windings? On the rotor or on the stator? You will prefer to put them on the stator here. Why? Not the rotor, because they will be very heavy. They are 3 larger diameters and also with more insulation. So it was before in DC machines on the rotor. Now the armature, because we have 3, they will be on the stator because of the size and weight. And the field will be at the rotor, and it's excited as before with DC current. So this is another major difference. The armature now in AC machines is on the stator and the field is on the rotor. What's the reason? The reason is that the armature now usually in practice is a 3-phase, so we need 3 windings. And the current is larger, so the wires will be larger, and the voltage is larger, so the insulation will be more. So we're gonna start talk about synchronous generators, and most of the generators in the system, they are synchronous. So if you go to the power plant here, for example, this is where we generate electricity, you will see that generators used, they are synchronous. So they are AC and they are synchronous type, not induction, which we'll cover next week. So we'll start with synchronous generator type, and after that we'll talk a little bit about the motor. So 99+% of all power are generated by synchronous generators. Synchronous machines can operate as generators or motors, so we'll talk first about the generator case and later about the motor. And we have 2 types of synchronous machines from structural point of view: round or cylindrical rotor, salient rotor. The cylindrical rotor is used for high-speed synchronous machines. Remember that for the generator case, the input is mechanical, so there will be speed. If the speed is very high, usually we use this construction or this type, which is called the round or cylindrical rotors. So we're talking about 1,800, 3,600 RPM, where the number of poles is low. If the speed is very low, relatively, we use the salient rotors. And this is usually in the case of hydroelectric power plants, where the inertia is high, but the speed is low. So we use more number of poles, and we use this structure, which is called the salient rotors. And we're gonna see both of them now. So in the round rotor, just give me